Welcome back as we continue our discovery of blood, and in this one we're going to learn all about the erythrocyte. So here are pictures, well actually on the right they're probably not real photographs, but on the left there is a photomicrograph of a red blood cell. And what you should be able to notice is that it looks a lot closer to a bagel or a bialy than it does to that round cell that you learned about when you were learning about characteristics of cells. So when we look at your blood, if we were to take out a cubic millimeter of blood, okay, so that test tube that you had blood drawn into is about 1 centimeter wide. So a cubic millimeter is 1/10 of that. So make a little tiny square, 1/10 of that all the way around. If you need to pull up a ruler and look at what a millimeter is. So a cubic millimeter or a cubic millimeter, they're the same thing, and that's what this mm to the power of 3 means. In that amount of space in your blood, there are 5 million erythrocytes. So even though, you know, we said your blood was only 45% formed elements, 5 million per cubic millimeter is a lot. And then I went ahead and I did the math for you. In that volume of blood, that cubic millimeter, that little tiny square of blood, that is 20 drops of blood. And so every time you bleed, if you have a drop of blood, you are losing about 250,000 erythrocytes in 1 drop. Okay, so let's get back to this erythrocyte and why it has this funny shape. Well, this shape has a name. It's called biconcave. So concave, like a cave, it goes in, and bi means it's doing this on both sides. So if we were to take the cell and flip it over, it would have the same depression on the other side. So if you go back to the pictures of the cell from our very first topic when we were learning about microscopy, look at the scanning electron micrograph and the transmission electron micrograph photos of erythrocytes, because that's where you can actually see the whole profile of it very carefully. So the reason why it has this shape is because it's missing stuff that it doesn't need. And as I alluded to previously, one of the things it doesn't need is a nucleus. Okay, so if it doesn't have a nucleus, there's a whole lot of stuff this cell can't do, including divide, right? Which means as soon as it's released into blood without a nucleus, it's in the process of dying. So think about that for a second. Are there other organelles that this cell would not need if it's not going to undergo mitosis? Well, yeah, there's quite a few. So there's no nucleus, there's no mitochondria, there's no RNA, there's no DNA, there's no centrioles, there's no centrosome. So as you can see, the list is quite long. And so what this does is it takes all this stuff out of the cell that the cell will never need. Otherwise, it'd be like carrying a refrigerator with you when you are going to the bathroom. You're not going to need your refrigerator in the bathroom. This cell's not going to need these things, so it got rid of it. And what this does, it actually makes this cell super flexible, which is fantastic. It means it can get in all the little tiny nooks and crannies. It's not just stuck on the main highways or even surface streets or even alleys or driveways. It can get through every tiny pathway, every size. So if it doesn't have all that stuff in it, what is inside an erythrocyte? Well, 90% of it is this protein known as hemoglobin. And so hemoglobin is not just one thing like here's hemoglobin. It is actually a bunch of things together. So if you look at the word, you can see it's broken down into hemo and globin. And globins, those were some of the proteins that we had. So globin is a protein. In fact, hemoglobin has 4 globin chains. As you can see, looking at this picture, There are 2 that are in shades of purple and 2 that are in shades of brown. And the reason for that is because there's 2 different types of globin chains in all of our hemoglobin. And attached to each of those globin chains is this thing that kind of looks like a UFO attached to it. And what this is a heme molecule. So here on the bottom right, this is what a heme molecule looks like. You don't have to know the chemistry of a heme molecule, but what I want to point out is what is in the center of a heme molecule, and that is this Fe, this red dot. Fe is chemical notation for the element iron. So there is an iron molecule in the center of every heme molecule, and that iron has a positive charge normally, which means something that has a negative charge would be attracted to it. And in this case, what is attracted to it is oxygen, which has a negative charge. Okay, so oxygen is going to bind to the iron in the center of the heme attached to each of the 4 globins, so that any one hemoglobin can have 4 globins, which means there's 4 hemes, which means there's 4 irons. Okay. So looking at the hemoglobin types, what we're going to be talking about is what we call adult hemoglobin, and that's what the previous picture showed, 2 alpha chains, 2 beta chains. This is what more than 90% of your hemoglobin is once you're adult. There is a second type of adult hemoglobin. We're not going to worry about that. When you were in utero, you did not have adult hemoglobin. Okay, it's called hemoglobin A, standing for adult, because you get it when you're an adult. So when you were in utero and you were a fetus, we took the F of fetus and we called it fetal hemoglobin. And that's because the beta chains had a different type of globin. And what that allowed was it allowed oxygen to bind more tightly, which was actually a benefit for you in utero, because it let you take more of your mom's oxygen from her hemoglobin, where it was looser with its attachment. Now, there are abnormal types of hemoglobin. Thalassemia is one type, and another problem with hemoglobin is our sickle cell hemoglobin, or hemoglobin S. Okay. Also, we can have abnormal hemoglobin when we inhale carbon monoxide. In that case, I'll get to sickle cell hemoglobin on the next slide, so don't worry about that. But I want to talk first about carboxyhemoglobin. When you are inhaling carbon monoxide, like for instance, if it's cold and you're trying to use your oven to warm your apartment, never do that because it's releasing carbon monoxide. And what happens is the carbon monoxide will bind to the iron in the middle of the hemoglobin, and its binding is 200 times stronger than oxygen, so it prevents oxygen from binding. So let's talk about hemoglobin and sickle cell. So the difference between a normal globin molecule and one with sickle cell is there is a 1 amino acid chain. A glutamic acid becomes a valine, okay? And that 1 amino acid chain you would think is not very important, but it is super important. But let's talk first about transmission. If you're a carrier for this, what this means is when you inherited, you only inherited the gene from one parent. So you have 1 normal gene and 1 abnormal gene. And so you're a carrier. You have what we call sickle cell trait. And so if you have a child with somebody who has normal hemoglobin, is not a carrier, whether you're male or female, you have a 50% chance of giving them your normal gene or your abnormal gene. And so we say about 50% of your children have a chance to have the trait, and 50% will be normal. Now the problem starts coming into being if two individuals who are carriers have children. Each of them could donate their normal hemoglobin and have a normal child. Or one could donate normal hemoglobin and one could donate the sickle cell hemoglobin, in which case you would have a child with the trait. Or both could donate the abnormal hemoglobin, in which case you have a child with what we call sickle cell disease. These are the people that have sickle cell anemia because they don't have any normal alpha chains. And so if two individuals who are carriers have children, they've got about a 25% chance of having a normal child and a 25% chance of having a child with the disease and a 50% chance of having a child with the trait. So what's the problem with hemoglobin S and this one amino acid chain is that hemoglobin S promotes sickling. And if you look at these cells that I'm pointing out, even without my glasses, you can clearly see these abnormal looking erythrocytes. And those are the sickle cells. Somebody with sickle cell anemia, because they have the anemia, they are actually kicking out the red blood cells faster than normal. So not only do you see sickled cells, you also see precursor cells being kicked out. So later on, when we learn about the formation of red blood cells, come back to this slide and try to determine which cells are demonstrated in that picture. So what's the problem with sickled cells? Well, they're not flexible. They can't get through all the nooks and crannies. So when a blood vessel splits to become an alley or a driveway, they get caught there and they block the road. And then that means all the other cells are blocking behind them, and you're actually going to be forming blood clots in your blood vessels, thereby preventing any blood flow from downstream, and all the cells downstream are going to start dying off. Any cells that are relying on nutrition coming down that pathway, there is no nutrition coming down that pathway afterwards. So it's a significant disease. And so this map kind of shows the worldwide prevalence, and then people look at the United States and they go, oh, 1%, cares, it doesn't really matter. You look at South America, oh, another 1%, no big deal. We live in the United States, we don't need to worry about it. But indeed, we do need to worry about it, and it's very important. If we look at our African American community, our Blacks, 8% of Blacks in the United States have the trait, which means they're carrying an abnormal gene. Okay. And all it takes is 2 of those 8%ers to make a baby to have a 25% chance of having somebody with the disease. So when we look at the incidence of sickle cell disease in the United States among the African American community, it's around 1 in 350 people. Okay. So about 0.3 to 0.4% of African Americans. And before you go, whew, thank God I'm not African American, for those of you who are not, and you think, oh, not thank God that you're not for any other reason, but for sickle cell, if you're Hispanic American, notice, if we look at the parts where there's Hispanics in the world, they also have sickle cell. So the incidence is much lower. It's about 1 in 15,000 as opposed to 1 in 350, which means there are carriers. And so if Hispanics with their certain percent of carriers are marrying Blacks with their certain percentage of carriers, you can't be surprised if you end up with a child that has sickle cell disease or grandchildren with sickle cell disease. So you're going, well, if sickle cell is so bad, because traditionally without modern treatment, the average life expectancy for somebody with sickle cell would be around the high school years. If you lived to your early 20s, you did really well. It was less than 10% of people that lived to their early 20s. And you're going, if that's so, Let's look a little closer at this darkness in Africa, where we have more than 15% of the population with the gene in places. You're going, well, if it's killing you in your 20s, how can so many people have the gene? And here's why. Because not only in Africa, but if you also look in the Gulf areas as well as India and other Asian communities, look at where these brown areas on this map, do you see how they correlate with the areas of the higher incidence of sickle cell? These brown areas are the areas that have a really high incidence of malaria, the organisms that cause malaria. And the problem with that is you start getting bit by the flies, the mosquitoes that carry malaria when you are an infant, when you are a child. So if you contract malaria, you can die at a much younger age. So if there's no treatment for malaria, then you're dying from malaria. And even though there's no treatment for sickle cell, you are living slightly longer. You are living to reproductive age where you are reproducing with other people who have the trait because they didn't die for sickle cell. Why aren't you dying from sickle cell if you have the disease? Because the organism that causes malaria lives inside the red blood cell, but it can't live inside sickled red blood cells. So if you have sickle cell anemia, essentially you can't get malaria. So you're not going to die from malaria, you're going to die from sickle cell, but you're going to make children with a high incidence of having sickle cell, and so the incidence of either having sickle cell disease or of the trait, so the incidence of the trait in the population goes up dramatically. So that was it for sickle cell. Let's get back to normal. Normal red blood cells. They travel to the lungs and they are going to pick up lots of oxygen molecules, which are going to be bound to the iron in the middle of the heme of the hemoglobin inside the red blood cell. And it's going to be carried all through the blood where it goes to the tissues, all throughout your blood, your little toe, your pinky, your earlobe, wherever. And it's going to be releasing oxygen there. Now, the first thing I want to point out, it's not releasing all 4 oxygens, okay? That hemoglobin, remember, we had 4 hemes, each one could carry an oxygen. In a typical one-time circuit, it releases 1, maybe 2. So even if you don't breathe, it can go around a whole second time, and there still is 2/3 to 3/4 of the oxygen still left. So this is why, like, your venous blood is not deoxygenated, it's partially deoxygenated. It's partially lost some of its oxygen. So it's going to release it to tissue cells. All right, now that you understand these concepts, let's try to put them all together. And I want you to stop the video and try to calculate how much oxygen is carried in any one erythrocyte. So go ahead and stop it. Okay, what kind of numbers did you get? This is where in class, I'm going to ask you what kind of numbers you got. Did most of you come up with 4? Some of you came up with 40. Some people come up with other numbers. They're usually multiples of 4. I asked you, can you explain? Sometimes I get 36, sometimes I get 360, sometimes I get where they have multiplied 45% of the cells times the 4, and you get whatever number that point, whatever 45 times 4 is. I get a whole bunch of different numbers. The problem is, if you're giving me 4, that's not per red blood cell. That's 4 per hemoglobin. And remember, I said hemoglobin was 90% of the red blood cells. So can you calculate it? Can you stop it and calculate it? Okay. So this is where I'm getting 36s from a lot of people, because you're going 90%. That's a 9 times 40. Or maybe I'm getting 360. You still can't calculate it because it was 90% of the cell, but I still didn't tell you how much hemoglobin. Each red blood cell contains 250 million hemoglobins. And by the way, HB, that's the abbreviation for hemoglobin from now on, capital H, lowercase b. Now you can do your calculations, and you don't need a calculator to do it. Because if there's 200, all right, stop it, figure it out. Okay, so coming back, 250 million hemoglobins. Each hemoglobin attaches 4 oxygen. What's 250 times 4? It's 1,000. So now you're doing 1,000 million. What's 1,000 million? A billion. Okay, so every red blood cell contains over 1 billion oxygens. And in 1 drop of blood, you're losing 250 million red blood cells. Okay, so I don't know what 1 billion is with 6 more zeros after that. It's like, can you realize? And that's in 1 drop of blood, okay? And then so you can realize how big this number will be for how much oxygen is carried throughout your body. So if you really thought that a red blood cell was only carrying 4 oxygens, you really need to stop and think what red blood cells are doing. They need to be able to donate a lot more than 4 oxygens. All right, so that's oxygen transport. Carbon dioxide transportation is different. What you have to realize that carbon dioxide, this is a waste product of the cells doing their jobs, their cellular respiration. And so what's going to happen is carbon dioxide is going to diffuse from an area higher concentration in the blood to an area of higher concentration in the cells to lower concentration in the blood. So it's going to diffuse into the bloodstream. And in the bloodstream, 7% will remain dissolved as plasma. You're going, why only 7%? All right. So have you ever been to a fast food place or any other place and you've ordered a beverage, a carbonated beverage, where they are taking, or if you've worked at one, where they are taking a syrup, the soda syrup, and mixing it with what? Carbon dioxide. And what is that mixing of the syrup and carbon dioxide do to the beverage? Makes bubbles, which go to the top. Do you want bubbles in your bloodstream? Of course not. That's why only 7% is dissolved. Excuse me. One more, sorry about that. So, which means there's 93% that's not going to stay in the plasma, but is going to move into the erythrocyte in the venous blood. Now, 23% of it is going to bind to hemoglobin. It does not bind to the iron in the middle of the globin. It binds someplace totally different. So carbon dioxide will bind to hemoglobin, and whether or not there's oxygen bound has nothing to do with whether or not carbon dioxide is bound. And whether or not carbon dioxide is bound will not influence whether or not oxygen can bind. So they're 2 totally independent processes. So that still leaves us the vast majority, the other 70%. What's happening to most of it? And what's happening to most of it, it's being converted. And here is the one chemical equation you're going to have to learn this semester. So learn it now. Carbon dioxide, CO2, is going to bind with water. Why? Because water is everywhere. And so we will never run out of water in a normal red blood cell. And so when it binds, what you need to do is add how many H's, how many C's. You can see there's only 1 carbon. There's only those 2 hydrogens, but this one has 2 oxygen, and there's 1 oxygen there, which means there are 3 oxygens. And so 2 hydrogens, 1 carbon, and 3 oxygens, H2CO3. That is carbonic acid. And so that's what it's converted into. But it actually doesn't stay in that, because the same enzyme that makes this also helps break it up. And what it's going to do is form 2 different ions. And so the first thing that's going to happen is we are going to lose a hydrogen ion, which is an H, and you have to put the little plus sign that shows it's an ion. And so if you subtract one hydrogen from the H2CO3, that leaves you HCO3. And because the hydrogen had a positive charge, that means that this now has a negative charge as shown by the minus sign. And HCO3 minus is a bicarbonate ion. Okay, so when a bicarbonate ion binds with hydrogen ion, that forms carbonic acid. Have you ever heard of bicarb before, as in sodium bicarb? Yeah, when sodium bicarb, that's a bicarbonate with a sodium. That's what baking soda is, for those of you who like to bake. Okay. So what I'd like you to do is look at this picture and talk yourself through this. So stop it, talk yourself through the process, and when you see the equation, you have to use the words, okay? So stop it and then come back when you're done. Okay, so to review, 7% of the carbon dioxide that's made by the cells travels dissolved in the plasma. An additional 23% is carried bound to the hemoglobin, which means 70% binds with water to form what? That's right, carbonic acid, which then will disassociate to form a hydrogen ion and a bicarbonate ion. And those things are going to affect the pH in the blood, because pH has to do with how much hydrogen ion there is. And so if this is in the blood, that affects the pH. So you can see where we'll be going later on in this course. All right, so what happens at the end of the red blood cell? Well, the red blood cells started from a stem cell in the red bone marrow, made its way into the blood where it circulated for around 120 days. In that 120 days, it's getting all dinged up. And at the end of 120 days, maybe it's 115 days, maybe it's 125 days. It's kind of like your backpack at the end of the semester. It's all dinged. It may have little rips, whatever. But the red blood cell is essentially non-functional anymore at the end of 120 days. And you can kind of get an idea what happens if you actually get a bruise. But what's going to happen is when that red blood cell near the end of its lifetime gets to the spleen in adults, liver and spleen in children, it will be engulfed because the white blood cells will recognize, hey, you're damaged, you can't pull a full load. We're going to get rid of you and replace you. And every single second, when you're awake or asleep, 2 million red blood cells are being phagocytosed by your spleen, which means every single second, 2 million have to be being kicked out from your red bone marrow. Because if not, then your blood counts are going to go down. So looking at what happens to that red blood cell after it's phagocytosed, it is recycled. It is not just destroyed. And so what's going to happen is, what you can notice is what happens to a bruise. When a bruise changes color, initially it's bright red, then it's kind of blackish, and then turns kind of greenish and yellow. And so what's going to happen is the globin is going to separate from the heme, and the heme, we're going to have the iron separate from the rest of this. So here is what it is all doing. The red blood cell has been phagocytosed, okay? The first thing that's going to happen is the globin is going to be broken down into amino acids, which then can be reused to make whatever kind of protein is needed, whether it's a globin or they can be split up to be made any other protein. The second thing is that the iron comes off of the heme and has a protein that it attaches to so that it can travel in your bloodstream, because it can't travel by itself. And so if you go back to the slide where it looked at what proteins were in your blood, you will notice that this protein was listed there. And then that takes it to the liver where it can be stored, or if the liver has adequate stores and you need to make some red blood cells, it will then go to the red bone marrow, where it will be used in the process of making new red blood cells, which then are released into the bloodstream. So we've dealt with the globin, we've dealt with the iron. So what we have left is the heme without the iron. And that gets broken down to a greenish compound called biliverdin, giving you that green bruise, which then turns yellow because of a compound called bilirubin that's metabolized to. The bilirubin is then carried in your blood to the liver, where it leaves your liver through something called bile. And then the bile gets secreted into your small intestine. And from your small intestine, it can be absorbed into your kidneys, where it gets further processing and then gets released in your kidneys, or it can continue into your large intestine, where it gets released into your feces. And this is what gives the dark color to your feces. So without it, you would have pale, pasty, oatmeal colored pale poop. All right. So that brings me to something called erythropoietin. And erythropoietin is a hormone that is made in the kidney. And it's made in the kidney when one of two things happens. Either your body has anemia or it has hypoxemia. So emia means blood, okay? Hypo means not enough, and the ox means oxygen. So hypoxemia means low blood oxygen in your blood. So let's look first what happens in anemia. Here we have inadequate blood. The kidney recognizes that, it kicks out the erythropoietin, which goes to your red bone marrow, and a process called erythropoiesis, or formation of red blood cells, occurs, which kicks out more red blood cells, elevating your red blood cell count, and so you have stopped the anemia thing. So this works by negative feedback. Once you're back to normal, it turns off the process. Similar process happens when you have hypoxemia, when you have hypoxemia, for instance, if you're trying to climb Mount Everest, you go to base camp and you acclimatize there for a couple of weeks before you make your attempt. And the reason for that is because you're at altitude. Here at sea level, we have about 21% oxygen content, but up there at altitude, it's a little bit less than that. And so your kidneys recognize that there's low oxygen in that. It kicks out erythropoietin. EPO is the abbreviation for erythropoietin. Does the same thing, travels to the bone marrow, stimulates erythropoiesis, a whole bunch of new red blood cells get kicked out, and then negative feedback will happen. And this, once you have higher levels of red blood cells, because now you have more oxygen in your blood. It also explains how blood doping works. Either you are taking more blood cells into your body, thereby increasing your red blood cell count, or you are being given synthetic erythropoietin, causing your red bone marrow to kick out a lot more red blood cells. I don't know why the red blood cells are blue in this picture. It doesn't make any sense to me, but they are. So either one of those drastically increases the amount of red blood cells in your blood. So the hematocrit, which is normally what? 45%, that's right. It's no longer going to be 45%. Now it could be 50 or 55%. And what's that going to do to the viscosity of the blood? That's right, it's going to turn it into sludge, okay? And so if you have this higher viscosity, and for instance, you're in the Tour de France and you're competing, you're doing an 8-hour bike rides, especially at altitude, and you're dehydrated as they go on. Essentially, at the end of the day, this totally explains why sometimes winners of that leg die that night of heart attacks and strokes, because their blood is sludge, because they've been blood doping. Not meaning to pick on Tour de France over other sports, but they did have a really high incidence of blood doping back in the day. All right. Now, let's talk about something that's a lot more common than blood doping, and that is anemia. And so when I ask people what anemia is, they always go, oh, iron deficiency. Okay, that's one type of anemia, but it hasn't defined what anemia is. Anemia is one of two things. This is a picture of the first type of anemia, which is where you don't have a normal amount of erythrocytes, as in you have a decreased number of erythrocytes. The second type of anemia is you have a normal number of erythrocytes, but you don't have the normal amount of normal hemoglobin. Okay? So either one of those things causes anemia, and the signs and symptoms of anemia doesn't really matter which way you're going of these, either the shortage of erythrocytes from any of its various causes or the decrease of normal hemoglobin from any of its various causes. What's going to happen is you have decreased your oxygen carrying capacity in your blood, so you are tired all the time. You can have pale fingernails if you have the shortage of erythrocyte types. So let's talk about the biggest categories of types of anemia. The one that is most common here in the United States is iron deficiency anemia. And it's a nutritional deficiency. You don't have enough iron. If you don't have enough iron, you can't carry enough oxygen. And so who is most prone for this? Women of childbearing age. Why? Because they have monthly blood losses that men don't have. And if you're not making a point of making sure you have iron-rich foods, not just spinach, but there's a whole bunch of other iron-rich foods, then you can become deficient in iron and you will be anemic. The other age group where this is a problem is the transition period from baby food to adult food where, okay, I can tell you right now, 18-month-olds don't say, Mommy, give me spinach, okay? Cheerios, okay? How much iron do you think there is in a McDonald's Happy Meal? Okay, there's a reason not to give them McDonald's Happy Meals, okay? And so they're the other age group where nutritional deficiencies become prevalent. Other common types of anemias are those due to hemolysis. Hemo meaning blood, lysis to cut up. So hemolytic anemias, these are ones where red blood cells are destroyed, which then is going to trigger this shortage of erythrocytes, which triggers the increased levels of erythropoietin, which triggers the erythropoiesis in the red bone marrow. And then a third type are those related to bleeding, which are your hemorrhagic anemias. For instance, if you have a really bad car accident, or you've had surgery, or you've had hemorrhage with childbirth. Okay, that's it for the erythrocyte. I want to thank you for continuing, and we will see you as we explore white blood cells next.